Hello, students. Again, Mr. Keister with you. Today we are going to continue our talk about equilibrium, and today we're going to talk about Kb in particular, which is the base dissociation constant for weak bases. In our last lesson, we talked about Ka, which is the dissociation constant, or K, for weak acids. As I look behind me here on our original do nows, these are Chem 2, by the way. This lesson would have been done on Monday, May 11th. Man, we're getting close to the end now. Actually, we're getting really close. All right, so this would have been done May 11th. Honors Chem would have been a couple days after that. But again, ignore that and make sure you're referring to the modified do now / calendar document that's located on my campus homepage. So, quick review from yesterday. So we looked at this chart here, right here, and talked about the K values for various acids. We noted that the K for strong acids, were extremely large, so large in fact that they are undefinable according to the rules of math, since we can't divide by zero. But we explained, or I showed you, that if the denominator in a K expression was extremely small, which means that the numerator was much, much, much larger, which is the case in strong acids, that you're going to end up with a K that is very, very big. All right, and like I said, in fact, so big in this case that it can't be mathematically measured. The Ks for other various weak acids are listed on this chart. And as we talked about, the magnitude of Ka, or the larger its value, the larger the value of Ka, the stronger the acid, since a larger value of K is going to mean that there are more products at equilibrium than there are reactants. And so as that value gets larger, you have more and more products. In the case of an acid dissociating or ionizing, you have more and more aqueous ions as compared to the original acid molecules. Notice this chart also has Kb values on it, and so they are on here as well. So let's clear out the do nows here, and there are our notes for today. So let's unfreeze the screen, and there we go. All right, so just as in acids, a base is referred to as either strong or weak, depending on the degree to which it dissociates or ionizes in solution. A strong base, just like a strong acid, ionizes 100% or completely. And remember, the strong bases include the soluble hydroxide compounds of both groups 1A and 2A. Of course, 1A are all soluble, and 2A, most of them are, remember, with a couple of exceptions. So I used a 1A hydroxide compound here as our example, sodium hydroxide. And again, since this is a strong base, we don't have an equilibrium arrow here. We have just an arrow in the forward direction. And so these ionize 100%. So again, if we just threw in a very quick ice chart here, and we started with 1 molar sodium hydroxide and no ions at equilibrium, if it ionizes 100%, then there'd be no sodium hydroxide molecules left over, which means a change of minus 1.00 molar. Again, with the 1-to-1-to-1 ratio, these would increase by that same value, and at equilibrium, these would be 0.110 molar. And just like last lesson with strong acids, if we were to set up a K for this expression, or for this equation, I won't do it today, but if we'd set up a K and throw in the equilibrium values, K would have been equal to 1.00 times 1.00 over 0, which again gives us an undefined value. But again, what does undefined mean? It means undefined in terms of how big it is. All right. So once again, the magnitude of K would be infinitely large, or humongous, okay? A weak base, such as aluminum hydroxide, only slightly ionizes in solution. So here's aluminum hydroxide. When it dissolves in water, it breaks apart into an aluminum ion, which has +3 charge, and 3 hydroxide ions, 3 hydroxide. So again, based on the fact that this is a weak base, this solution contains very few aluminum ions and hydroxide ions at equilibrium, and nearly all aluminum hydroxide molecules. All right? Weak base works the same way as weak acid. So let me advance the page here, and we will talk about weak bases in particular, and talk about our equilibrium constant for those, which is called Kb. So many substances behave as weak bases when dissolved in water, not only hydroxide compounds, all right, but also others. And we talked about those back in Unit 11.1 when we talked about Lewis acids and bases and Bronsted-Lowry acids and bases. They don't necessarily have to have hydroxide ions in the compound, but when they're dissolved in water, they can produce hydroxide ions. And we'll look at that here. So here is ammonia, all right? Ammonia in solution. Remember, ammonia is normally a gas, right? But ammonia in solution acts as a weak base. It's basic, all right? When you react it with a water molecule, and again, we're going to look back at Bronsted-Lowry acid-base theory here. So a base, according to Bronsted-Lowry theory, is a substance that accepts a hydrogen ion or a proton, all right? Ammonia here acts as a base, which means that water now is acting as an acid. And again, a Bronsted-Lowry acid donates or gives up a proton or hydrogen ion. So how do we know ammonia is a base? Because over here, the ammonium ion is formed, all right? So that would be our conjugate acid. Remember, once a base accepts a hydrogen ion, what is formed is its conjugate acid. Here then is our acid-base pair. And water acting as an acid is the donator of that hydrogen ion that ammonia accepted. And what's left behind from that acid, once it donates a hydrogen ion, is called its conjugate base. And as you can see, the conjugate base of water is the hydroxide ion, all right? So this is then the equilibrium equation for the formation of sodium hydroxide, right? Sodium hydroxide is soluble, of course, and so these are split. So even though NH3 does not contain hydroxide ions per se, when it is dissolved in water, hydroxide ions are produced from the water having given up a hydrogen ion to ammonia. And so let me talk about that. So real quick. So normally, I want you to notice that when ammonia accepts that hydrogen ion, we write it as NH4 plus 1, which we, of course, recognize as the ammonium ion. However, if it wasn't an ion that we already would regularly recognize, I wanted to tell you that if you look at how we did this, you notice when we added the hydrogen ion to ammonia, we didn't write it this way, HNH3 plus 1. We didn't write it like that. So normally, and this is the standard rule, the hydrogen ion is added at the end of the base. Okay, normally added at the end. Occasionally, I will see in a book where they have put it in the front, but again, if we had done it with ammonia, it looks like this, which doesn't seem right. All right, so and so it's written this way, where the hydrogen ion is latched onto the end of the original base molecule. And normally that's the way it's done for all bases as well. So wanted to throw that in there. All right. The equilibrium expression for this reaction. So if we write K for this, again, it's products over reactants. So this would be our ammonium concentration, our hydroxide concentration over our ammonia concentration. And then what about this one? Does water go in there? If you're shaking your head, no, you're right. All right, remember, pure solids and pure liquids do not appear in K expressions because their concentrations remain unchanged. All right, their concentration is based on their density. Their density it remains unchanged. Remember, it's an intensive property. It's independent of quantity, and so as is its molar mass, and so thus its density and molar mass being constant, you can derive concentration from those two constants, and it would, of course, then also be a constant. We've talked about that before. So this then would be K, only now it's called Kb, all right? Notice that there is not a shortcut dissociation reaction for a weak base. Remember, in an acid, we had the real one, we had the shortcut one. In a base dissociation, there is no shortcut, all right? So in other words, when you are given a weak base, you must add a water molecule to it, and then remembering Bronsted-Lowry, that base accepts a hydrogen ion, which we will latch on to the end of it, and then what's left behind from the water is the hydroxide ion, which is the source of the hydroxide ion. All right, so don't forget that. No shortcut. All right, no shortcut. So H2O, put that up here too. H2O, not included in K expression. In this case, it's Kb, but if it was any other K, it wouldn't be in there either. All right? So K is now known as Kb and is called the base dissociation constant. The calculations involving Kb, hydroxide concentration, and pOH are all analogous to Ka, hydrogen ion concentration, and pH that we went over in our last lesson. So this is going to look very, very similar to that. Okay? So this is kind of a review of Ka, only now it's Kb. Okay? Because the calculations are done virtually the same. All right. So this one asks us to calculate the hydroxide concentration, the pH or the pOH, and the pH of a 0.150 molar solution of ammonia. Here is the Kb for ammonia, 1.80 times 10 to the minus 5. All right. So we'll write our equilibrium equation. Remember, for a base, there is no shortcut. We have to add the water molecule to it. And again, when the base accepts a hydrogen ion from water to form its conjugate acid, that hydrogen ion is put on the end. All right. So again, we recognize that for this particular one, that would be the ammonium ion. All right, that would be the ammonium ion. And then the hydroxide ion is going to always be the other product in a base dissociation equation. Again, the hydrogen ion from water latches onto the end of the base. The hydroxide ion is the other product. Okay, it'll be that way every single time. Okay, so we'll set up a nice chart here. Longer. Okay. We have a 0.150 molar solution of ammonia initially. These, of course, are 0. Water does not play a role in the K calculation. Don't need it. All right? Don't need it. Okay, so we are given KB. Okay, we are given KB. We are not given a pH or a POH or anything like that. So we got nothing else to go on as far as filling in our equilibrium row of values. So again, we know this goes down and these go up. This goes down by some value X. These go up by some value X. So in equilibrium, 0.150 minus X molar, X molar here, X molar here. Again, hopefully after yesterday's lesson, you are not now hyperventilating or sweating profusely upon seeing this down here thinking, oh no, we got to do the quadratic equation. No, we don't, all right? Because the same rules apply for weak bases as they do for weak acids. And that is, all right, if Kb is less than or equal to 10 to the minus 4th. Doesn't matter what times 10 to the minus 4th. Well, it could be 1 times 10 to the minus 4th. It could be 5.5 times 10 to the minus 4th. It doesn't matter. As long as it's 10 to the minus 4th or smaller, all right, then no quadratic equation. All right, no quadratic equation. So, good news again. All right, and if we look at Kb's value or the ammonia's Kb value, 1.80 times 10 to the minus 5th, smaller than 10 to the minus 4th, that means we're good to go. Which means we can scratch that minus x out of there as long as we make a qualifying statement. X is small as compared to, so yesterday we compared it to the initial acid concentration. Today we'll compare it to the initial base concentration, 0.150 molar. When you make that statement right there, you can scratch those x's out. Now let me tell you, and I've seen this done on the AP exam. If you forget to make this statement, glad I remembered that because I forgot to tell you that yesterday. If you forget to make this qualifying statement right here, and you go ahead and scratch those out and calculate it the short way, they'll count it wrong every time. All right. Without this statement, those x's do not disappear, which means you have to calculate x's value using the quadratic equation. So, your choice. You can take 5 seconds and write this down and scratch those out, or you can take 5 seconds and forget to write that down and take an extra several minutes to run the quadratic equation to solve for x. Personally, I'd rather do that. All right? Okay, let's do Kb now. Is the concentration of ammonium, concentration of hydroxide over the concentration of ammonia. Remember again, water is not in there. And so we have a value for Kb, 1.80 times 10 to the minus 5th equals x times x, or x squared, over 0.150. And again, without that minus x there that would have been there had we not been able to do that, we'd have been running the quadratic here shortly. But since we don't have to do that, then that's not necessary. So we have x squared then equals 1.80 times 10 to the minus 5th times 0.150. So multiply those two and square root it. Now this is asking us for our concentrations in equilibrium, so we can go ahead and round these and to 3 sig figs. 1.64 times 10 to the minus third molar. Okay? So, our equilibrium hydroxide concentration, which is asked for, is 1.64 times 10 to the minus third molar. Okay? It did not ask for the equilibrium ammonium ion concentration, but as you can see by the 1-to-1 ratio, it would have been the same. All right? So it's also equal to the equilibrium ammonium concentration. Like I said, it wasn't asked for, but had it asked for that, we would also have that answer. And it did not ask us for the equilibrium ammonia concentration, but we got that too. What is it? Well, it's still 0.150. Again, that was not asked for, but if it had been, we have that value as well. In other words, remember, this one is unchanged. Obviously, it did change a little bit, but not significantly. All right? That change is negligible based on the value of Kb. So, it asked for POH. Okay? So, POH is equal to the negative log of the hydroxide concentration, which we now have. So the negative log of 1.64 times 10 to the minus third, and the 3 sig figs, that POH is 2.79. And then it asks also for the pH. And so the pH of that solution, of course, is 14 minus the POH, 14 minus 2.79. And again, this is a constant. So since this is 2 decimals, that our pH would be as well, 11.21, which you can see is, of course, basic pH, right? Or basic POH, however you want to look at it. So again, these calculations here were very, very similar to the ones we did on the last lesson involving weak acid calculation. Now that's the only example I'm going to do today, since they are very similar. However, I would remind you, or I'll show you, that on our assignment that goes with this lesson, which is equilibrium number 9, weak bases and Kb. All right. Question 1, if you'll get that out. Question 1, let's see if I can maybe pull that up real quick. I think I can, reasonably fast anyway. Let's see. There it is. Yeah, there it is. All right, so let me erase this real quick. I did want to bring this up since we didn't do an example like this today, but we did in the last lesson over weak acids. So in number 1, talks about ephedrine, which is a central nervous system stimulant. Ephedrine is found in a lot of cold medications. Right? It is used in nasal sprays as a decongestant. This compound is a weak base and has the formula C10H15ON. All right. A 3.50 times 10 to the minus 2 molar solution of ephedrine has a pH of 11.33. All right, I'll do a little bit of this one with you. All right. I'm not going to do all of it, but at least get you started on it. So let's write the equilibrium equation for this base. So remember, for Kb, there is no shortcut in writing the dissociation equation. We have to add a water molecule to our base. So here's the formula for ephedrine, C10H15. That's 15. Where is it? Oh, there it is. Yeah, H15ON. ON, AQ. Now we're going to add a water to that. So remember, the base accepts the hydrogen ion from the water molecule. So again, we add that hydrogen ion normally on the end. So it'd be C10, H15, O, N, H plus 1, AQ. And then, of course, hydroxide ion is always the other product, since that's what's left behind from water after it donates to hydrogen ion. So there's our equilibrium equation. It asks us to determine the equilibrium concentrations of all species, of all substances. And so you would do an ice chart, of course. So we start out at 3.50 times 10 to the minus 2 molar. All right. These, of course, are 0. Water doesn't matter. It's constant. Okay. Now, here we are given a pH. So we are going to be able to get an equilibrium value of hydroxide concentration based on that pH. All right. But remember, we can't get hydroxide concentration directly from pH, but we can get it from its POH. All right. So let's look at that real quick. I'll put it over here. So the POH then would be 14 minus the pH, which would be 14 minus 11.33 or 2.67, I believe. All right, 2.67. And then we can get our equilibrium hydroxide concentration, because that's equal to 10 to the negative POH. So 10 to the negative 2.67 to 3 sig figs is 2.13796,209 times 10 to the minus third. Now notice I didn't round that because we don't round in the ice chart, but when we give our answer, we can round it. So this is our equilibrium hydroxide, 2.13796,209 times 10 to the minus third, which means that's how much we added here, same amount. And again, since we're looking at a 1-to-1 ratio here on all these, we would be adding that same value here, subtracting that same value here, and then we would have all of our equilibrium values down here, which since it is asking for those, then when we write our answers down here, we can go ahead and round them off to 3 sig figs. So that'd be 2.14 times 10 to the minus third molar. But again, we don't do that in an ice chart. And then finish off the rest of the stuff like we did with weak acids. So that is a little different calculation involving Kb. The one on the backside, problem 2, is set up just like the one we did, I think, on the notes. So I would tell you this. It asks you on part D, on number 2, to find the percent ionization of a base. It's the same equation as finding a percent ionization for an acid. We're just going to substitute in acid for base. So I'll write that over here. So when you get to it, so the percent ionization is now equal to the equilibrium hydroxide concentration. Remember, for an acid, it was hydrogen concentration over the initial base concentration times 100. So again, it's the same equation as acid, only we're substituting in hydroxide for hydrogen ion and base for acid in the equation. Otherwise, it's exactly the same. So I believe that's all for today. So like I said, very, very similar calculations and scenario as it was for a weak acid. The only difference is, remember, we do not have a shortcut way of writing a base dissociation equation. We must add a water molecule to our base and then run it through the real way, because that's how it happens. Okay, so that takes care of today's lesson over weak bases in KB. You should be able now to finish equilibrium number 9. All right, and that would be your homework for this lesson. So until next time, this is Mr. Keister signing off. Everybody take care, stay safe, keep working. We're almost to the end. So the end is in sight, and keep after it, and catch you next time. Bye, everybody.